I certainly don't claim that JavaScript is the language that we should be writing in, but I think it's a pretty nice language if one ignores 95% of it. And I think it's good for us as a community to be exposing, if there's a funnel, well, JavaScript is like the big end of the funnel. And if we all immediately switch to Haskell, PureScript, things like this, and start just evangelizing those languages, we're not really going to increase the size of the functional programming community all that much, because people generally don't go from, animating a div with jQuery to like GADTs in Haskell or something like that. It's going to take lots of steps. Hey, we haven't started yet, so. Oh. What do you think? Shall we get started? Okay. Yes, so hello everyone. My name is David, and yes, I'll be giving this workshop, and it's all about dealing with uncertainty. It's something that we all need to deal with regardless of the language. Some languages make it easier than others, and JavaScript tends to be a language that just encourages us to, program the happy path and just have runtime errors for everything else. But we can do better than that. Yeah. Please do ask questions. I think that this is actually going to be quite manageable, the amount of work that we have in front of us. So there should be time for, a few tangents. So please do stop and, call out if you have a question or if you think there's something interesting that we should discuss. So, yeah, if you want to follow along, all you will need is some version of Node and some version of NPM. And if you don't have Node installed, you can easily use the website, which I will show you in a second. So the one dependency we're going to install is Sanctuary, but that's a bit of a lie because it's actually going to bring in quite a few dependencies, all Sanctuary dependencies. And let's just go into the Node REPL. You haven't missed much, just starting up the REPL. Okay, so let's go ahead and just require these two packages. The names that we give them don't really matter, but these are the conventional names for these two modules. Okay. And yes, if you would like to follow along and you don't want to use the Node REPL or don't have it installed, you can simply jump to any browser and go to sanctuary.js.org. And I'll show a couple of things because, well, they might not be obvious. The first thing to know is that we can just put the function name in as an anchor fragment and jump to that particular function. It's a nice way, if you know exactly what it is that you're looking for, you can get there straight away. Otherwise, there's a table of contents at the top, but there are 100 or so functions, so it can be hard to find. Anyway, so all of these examples are editable, so we can just type in arbitrary JavaScript expressions and evaluate them. And Sanctuary is, of course, loaded into the context, so all of the examples that you'll see on the slides could be run in any one of these mini REPLs. And the other thing is that if you want to write something longer than one line in the browser, you can, of course, go into the browser console and you could concat foo and bar and get the result. Anyway, So hopefully, if you do want to follow along, you have some way of evaluating JavaScript expressions. For the most part, I'm going to try to stick to sort of this setup here and not flick back to the browser too often. But feel free, of course, to have the website open and jump to any definition that looks interesting as we walk through. So,
what was the prerequisite before npm?
All you need is Node.
No.
Yes, so you can download it from the Node.js website, or you can probably use a package manager. You can brew install Node, for example. Okay, so one thing that we like when working with functions is we like types. And this is a little feature, which is that we can actually tap into the REPL's sort of inspection mechanism. So all the functions in Sanctuary have these type signatures. And the way to read this type signature is words is of type string to array of strings. So that simply means that it's a function that takes a string and it's going to return an array of strings. So let's look at an example. As you would expect, we can give it some string, foo baz, and get back, in this case, an array foo bar and baz. Nothing too exciting here. I just wanted to choose a function to sort of introduce type signatures. And we'll see some functions a bit later on that have some even more interesting type signatures. So JavaScript is a language that isn't going to stop you from doing anything. And of course, we can apply functions to anything that we want to. So we could apply s.words to null. So what would you like to see happen in this case? What would be a sensible thing for us to do? So maybe the JavaScript thing to do would be return undefined or something. Because in general, the JavaScript way seems to be just do your best, and if you can't succeed, just make something up. But we get an error. So this is a runtime type error. But it is quite helpful. It tells us, well, okay, the first argument to words is meant to be a string. You gave me null of type null, and it's not a member of string. Maybe you want to go to this URL to read the documentation about the string type. We can probably guess what the string type is from its name, but for other types, maybe your own custom types, they might be more interesting and less guessable. But anyway, this for me is progress. Having our program crash is definitely a good thing. When we make a programming error, we'd like to fix it rather than have it maybe silently succeed or fail. So let's look at a function that has a more interesting type. So it's called parseInt. So JavaScript has a function called parseInt, but this is slightly different. So the first thing to note is that there are two arrows in this type signature. And the way to read that is parseInt is a function that takes an argument of type radix, and it returns a function from string to maybe integer. So think of it as a function that needs two inputs, and it receives those one at a time. And so what would happen if we were to apply s.parseInt to 16? And I'll just tell you that 16 is a valid radix value. It can be anything between 2 and 36, I think. But what sort of result would we expect in this case? Well, the function takes two inputs, one at a time. Did you want to? No? Okay. So we're giving it the radix, but we haven't given it the string yet. So we get back a function. It's waiting for the string that we're trying to parse as a hex value. So let's look at some examples. So let's try parsing something that we know to be a valid hex value. Okay, let's see what we get back. Just 42. So the fact that we got back a just indicates that our operation was successful, and the result of the successful operation was 42. But let's try giving it something silly, like boulder. That's not going to work, and neither is some other thing that's not a hex string. So we have these things. We'll get into what just and nothing are all about. But so far so good. We haven't resorted to, making things up. Just partly for the fun of it, let's look at some JavaScript equivalents. So this is using the built-in parseInt function in JavaScript. It's similar. It takes 2 arguments, and it's totally usable in the case where you provide it with valid input. In this case, it gives us back 42. So far, so good. Does anyone want to guess what boulder is going to give us? Well, this is really making fun of JavaScript, which is not the intention of this talk, but it gives us 11. And that can be an exercise for you to figure out why that might be 11. JavaScript, it's all powerful. If we give it XXX, well, that gives us nan. So boulder is 11, but XXX is nan. So yes, figure that out. So the maybe type saves us from throwing an exception or returning a bogus value. And by bogus value, I mean something like nan, null, undefined, empty string in some cases, -1, which you'll be familiar with from Java style index of operations. So yeah, we can avoid bogus values. And I love this fact. We can avoid philosophical discussions because I don't know how many hours of people's time has been spent discussing what the correct result of taking the head of an empty array should be. It's philosophical, there's no correct answer, but it then goes into debates where people say it should be undefined, people say that's the idiomatic result, other people say it's better to throw an exception, and really there is no answer. There's no element, so we should talk about things that can actually be resolved. And that's what head will help us to do, because the type of head is a little bit different from even the head function in Haskell. So people talk about Haskell as a pure functional language. It doesn't seem quite pure, because quite a few of the functions do blow up at runtime. Anyway, so this is the head function that Haskell would probably have if it were to be designed today. You can see that the return type is not A, because we don't necessarily have a value of type A if we're given a value of type array A, because empty array doesn't have any A's inside it. So rather than lie and say that we're always going to return a value of type A, we're going to be honest about the fact that we might not be able to provide a value of type A. And so this is the way the maybe type would be defined in a language like Haskell. So we say that we have a type, which we're going to call maybe, and it takes a type argument, which we're going to call A. And the way that we create one of these maybe A values is either by using nothing. Nothing is polymorphic. It's much like the empty array is both an array of strings and an array of numbers at the same time. Nothing is both a maybe string and a maybe number, maybe whatever you can fancy. Or we use the just function, which is a data constructor that takes any value and returns us a maybe of the same type as that value. So just 0 is going to give us back a value of type maybe number. And this is a little bit of a lie because there's no rule that says that a value can only be a member of one type. Just 0 could be a member of maybe number, maybe integer, maybe non-negative integer, as many types as we would choose to define. That's a little bit out of scope for this talk. But yeah, maybe number is a fine approximation. So how do we operate on a value inside a maybe? So the thing that was so convenient about, the built-in parseInt function, and let's say we have a list which is going to contain foo, bar, and baz. Well, the JavaScript way to get the first element of that list would be to do this. And why is that convenient? Well, that's convenient because we know how to operate on strings. And if we wanted to, say, convert that to uppercase, we would just, just chain the operations together. But of course, the problem would be that that expression would blow up if the list were empty. So we're going to need a different approach. And it turns out that we can use map to perform these operations. So let's use map. It's going to take two arguments. The first argument is some function that we want to apply. So in this case, we'll use the toUpper function that Sanctuary provides. And let's map over just ABC. Any guesses as to what this is going to give us? It gives us just ABC. So it's taken the value out of the maybe, applied the transformation, and put it back into the maybe context. So another example would be if we had nothing here rather than just ABC. Well, the result has to be nothing because we don't have an inner value. We don't have a string that we can give to the uppercase function. But what's really cool is that map is a very general function. So we can map over arrays, and I certainly had a mental block for quite a long time. I had got into programming through Python and JavaScript, and I had somehow wired it into my brain that mapping is something specific to lists and arrays and that sort of thing. But it's a more general operation. So this sub function is just the subtraction function. So this is going to give us a function that subtracts 1. And let's give it an array 1, 2, 3. And we've simply subtracted 1 from each element in that array. So nothing too surprising there. But what about this? Well, it turns out that if we treat JavaScript objects as string maps, we can do the same thing. So all I'm doing here is changing the data. I'm still using the same map function and the same transformation function. Now if we try to decrement all of these values, we get back a string map with the same keys, and all the values have been reduced by 1. And yeah, this is what we were doing just a moment ago. We can change this data value from a string map to a maybe number, and we get back a maybe number. This is really nice. And this one, this is pretty mind-bending, I think. But it turns out that what we can do is replace the data argument with a function. And we get back a function. And this is a nice property of map. We always get something, we get back something from map that has the same structure as the thing that we started with. So if we map over an array that has 3 elements, we'll get back an array that has 3 elements. If we map over a string map that has, 3 key value pairs, we're going to get back a string map with 3 key value pairs. And if we map over just, we'll get back just. If we map over nothing, we'll get back nothing. Turns out if we map over a function, we get back a function. And this actually allows us to perform function composition. What this is going to do is compose the subtraction function and the absolute value function. We'll feed in the input, which is -8. We'll convert it to the absolute value, so we'll get 8. And then we'll subtract 1, and we'll get 7 as the answer. So it turns out that if we have map we don't need a special function for doing function composition because map naturally performs function composition for us. It's still nice to have a function called compose or something like that because it's a lot more obvious what's going on. But it's pretty cool that map can even map over functions. And at this point, I was going to do something in Vim, but since I have a blackboard, I'll do it here. And all I'm going to show is how we can specialize a type. So if we look at a general type, like the type of map, it has a really general type, which is it takes a function from A to B and an f of A and returns an f of B. And there's one thing that I forgot to mention up here, which is there's some constraint on f. We can't just put any old type in place of f because only some types will allow us to map. But what we might want to do is say, let's replace f with array. And now our type would be A to B to array A to array B. And we could do a similar substitution. This time we could replace f with maybe. So what's nice is that we get this whole family of functions all in one. And each of these functions is itself polymorphic. So we could say, oh, we have an array of strings, and we want to map over that and get the length of each string. So, okay, we want A to be string, and we want B to be integer. So map allows us to do that. And these general type signatures can be a bit intimidating because it looks like a lot of letters and it's hard to get a handle on anything. But if you decide to start programming with these sorts of functions, it's really nice to be able to perform these substitutions in order to understand, well, okay, if I pick this type in the place of this placeholder, this f, for example, what will be my concrete type? So function composition limits complexity. I think everyone in the conference really is beating that drum. But beyond that, I would say that function composition is more important in Sanctuary than it is in Haskell even. It's not just the way that we limit complexity, it's also just the way that we build our programs. So we don't have a compiler to nudge us in the right direction. So what turns out to be a really natural way to program with these libraries is to build the program one step at a time and to check our work as we go. And there's a particular function in Sanctuary which makes this really natural. So this is the only function in Sanctuary that has a made-up type signature. Well, yeah, it can't really be described. I don't know how it would be described in Haskell because it essentially takes an array of functions and it produces a function that's going to take an input, feed it into the first function, take the output of the first function, feed it into the second function, and so on, and return the output of the last function. So the reason that I couldn't write a signature for this in Haskell is that we're essentially taking an array of values of different types, because we could have a function from, say, string to integer, and then a function from integer to integer, and then a function from integer to maybe integer, and then a function from maybe integer to string. So we're composing things that don't have to be things of the same type. Anyway, all the other functions in the library have, I guess, Haskell-approved types, one might say. But pipe is sort of the odd one out. but it's so useful that I wouldn't want to give it up. So this is really the way that I start a function when I'm writing something with Sanctuary. So what I'm going to do is jump out of the REPL, and let's just create a small little JavaScript file for us to play in. I have no idea whether useStrict is going to help us here at all, but I've been trained for years to always start files with that. So that's what I do. So we're just going to require those two libraries, Sanctuary as S and Sanctuary def as $. And we're going to define this really silly function, f. It's a function from A to A because it's an empty pipe. All it does is just return its argument. The other thing I'm going to do is I'm going to write a little function to make it easier for me to actually check my work as I go. This is just a throwaway function. Let's just call it test. And test is itself going to be a pipe. And the first thing we're going to do is we're going to provide our input as an argument to f and get back whatever f gives us. We're then going to use this function called show, and that's going to give us a nice string representation of our value, so that if we have a value such as just ABC, we'll get back just ABC, something that we could type back into the REPL, say, rather than whatever JavaScript internals that value happens to show us if we were to console log it directly, and then we'll just log it. So that's all we're going to do with test. Test isn't going to change, and now let's actually test our function. So we're going to give it some input, and I don't know. I'm just going to give it some input here, and then if we run this, we just get back what we put in. So we gave it the string, and we got back the same thing. But we've sort of set up this nice environment in which we can easily add another operation to this set of transformations. So let's say that actually what we're going to do is we're going to use the words function that we looked at before. And so all we're going to do is take the value that the pipe receives, give it to words, get back the result from words, and then return it to the caller of f. So no longer do we have this A to A function. It's no longer the identity function. The type of f is now the type of words, which is string to array of strings. And now if we jump back to here, I'm actually going to provide something a bit more interesting here, foo-bar-baz, as we had before. Now if we run our program, you can now see that we're getting back an array of strings. No surprises there. All I'm doing here is showing you this is the way that I go about building things up step by step. So let's say that we want to get the length of each of those strings. So we want to use map to apply a transformation to each word. So we're going to map over our array of words, and for each word, let's make it explicit. For each word, we're going to return word.length. So let's see what that gives us. 333. All those words have a length of 3. So Sanctuary provides a function for doing these lookups. If we want to essentially assert that length property is going to be there, just in case we made a typo, say, this might just give us undefined, undefined, undefined. So what we could do instead is we could use the prop function that Sanctuary provides. And the way that works is you give it the name, the property name that you're interested in, and you give it an object, and then it returns you the value of that property. Now, if that property doesn't exist, that is essentially a programming error. Now there's a sort of cousin function of prop that's designed for situations in which we can't be sure whether something's going to exist or not. But prop is a function that we use in cases where we really expect that to be there. And if it's not there, we've done something wrong and we want to know about it. So let's run the same code with the same typo. And this is just to show that, hey, prop expected the object to have a property named length misspelt, and it doesn't. So we can easily go in and fix that now. Run that again, and we're back to having 333. Okay, let's say that we want to take, oh yeah, go ahead.
Is prop essentially like a lens?
So the nice thing about a lens is a lens provides a way to both read a value that's somehow inside something else. So for example, the value of a particular property, but it also provides a way to update that value in a mutation-free way. Whereas prop is just doing the reading. So we could actually define prop in terms of a lens, but we couldn't define a lens in terms of prop. So this is sort of the weaker thing. And I'm hoping that Sanctuary will soon have lenses because they are pretty nice. But anyway, let's get the square root of each of these values. And again, same thing. We now have an array of integers, and we want to square root each of those values. So we can use the square root function. And I'm going to change the test input because this one is not so exciting because they're all of the same length. Let's change this to I love pipelines because I definitely love pipelines. And we now get 1, 2, 3. So we started with the string I love pipelines. We broke it up into words. We had an array of words, which we then transformed into an array of integers by taking the length of each word, 1, 4, 9. And then we turned that array of integers into an array of numbers by taking the square root of each one. And let's say we wanted to get the sum of those. Well, nothing fancy. Just take the sum, and we get 6. So what I love about this way of working is I essentially have a working program at every point. F might not do what I want it to do initially, but I can build it step by step. Now, one thing you may note is that I had this type signature for F, which of course is no longer up to date. And this is of course the big drawback to using comments. They can easily get out of date. But I would argue that it's still better to have a type signature that may be wrong some of the time than not to have a type signature at all. Okay, so I have a challenge. This is a warm-up challenge, I guess. And yeah, I've put an alarm to go off in 20 minutes so that we can have a short break, because 2 hours is a long time. So we'll have a 10-minute break in 20 minutes time. But anyway, let's try this challenge. We want to create a 2-dimensional array of all the words in all the lines of a string. So let's say we have a text file, and we've read that text file. We now have a string that has the contents of that text file. It might have, say, 10 lines, and each of those lines has some words in it. And we want to get back a 2-dimensional array that is essentially going to have the same structure, where we have an array, and here are the words from line 1, and here are the words from line 2, and so on. So we want to preserve the structure. We don't just want all the words from the file all in one array together. So Sanctuary provides this this lines function, which is pretty handy. So let's just go back into the REPL. See how lines works. So this takes a string that has maybe some new line characters in it and gives us back the lines with the new line characters removed. So the question is, let's change the input here to be something a bit more realistic. So let's say that the first line is going to have ABC, the next line is going to have D and E, and maybe the next line just has F and G, let's say. Okay, so now we have this string, this array of strings, and we want to turn each of those strings into an array of words. So how might we go about doing that? Any? Okay, so tell me what you want me to write. S.map of.
Well, you need to pipe S lines to S map of S prop split.
Okay, so you're saying we want a pipeline, and you're saying the thing that we want to start the pipeline with is lines, and then we want to, you were saying map?
Map over the result and split them.
Okay.
S prop split or whatever.
Okay. Yeah, so we can actually use, you're totally onto it, we can use the words function that we looked at before. That's going to give us all the words for a given line. And so now we can apply it to our input. And yeah, in this case, we don't necessarily need, in the REPL, pipe is sometimes a bit less convenient, so we could actually sort of move this around a little bit. So we want the lines of our input, and then we want to map over the lines with words, and we get back this two-dimensional array, which is what we want. So nicely done. Yeah.
Regarding the pipe, so I imagine that I built like a large transformation with this pipe.
Yeah.
What if I want to return and then inspect like every line? So now we have this test which prints everything. Comparing to the initial input, the output can be completely different.
Yes.
Just inspect step by step.
Right. Great question. So this is both a, I would say this is both a good thing and a bad thing. So some people will point this out as a problem with using these pipelines is, well, it can be tricky to debug them because there's nowhere for me to sort of insert console.log or whatever. But in a way, they're actually easier to debug, because what we could do is we could define a function, let's call it tap, and all tap is going to do is allow us to log a value and then return it. So we'll just take some value, let's call it x, and let's console.log x and then return x. So I was in a talk earlier which was talking about how Elm uses the same trick to essentially allow people to log things without the type system knowing about it. And the nice thing is that because it just passes through the value, we can insert this anywhere into the pipeline. And in fact, we might be better off using s.show of x so that we get a nicer string representation. And now we could actually, if we wanted to, just do this. Tap, 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 tap. And now if we run this code, we should see the whole sequence of transformations. Our original input, I love pipelines. We then see it broken into words. We then see the lengths of those words and the square roots, and then finally the sum. And we see 6 twice because we logged the return value, and then we returned it and logged it again. So yeah, excellent question. And yeah, tap is pretty handy. Sanctuary doesn't provide tap because it's impure, and so it's sort of against the spirit of the library, but it's really easy to define it oneself. Let's go back to the REPL. Okay, so we solved the challenge pretty nicely. So this is the solution that we might write if we already have the text available. But more often, we're going to write it this way, where we're defining a function which, will receive the text at a later point in time. And for simple compositions, it can seem like overkill to use pipe, but I really like it for anything beyond more than say two functions, because it reads from top to bottom, and we get to put each transformation on a separate line. So okay, this is where things get more interesting. How would we create a one-dimensional array instead? So before we had an array that contained an array of words for each line. But what if we wanted to essentially get rid of these square brackets and just have a single array of words? Concatenate? Yeah? That's totally the way that we would go about it. So there's also a sneaky answer, which is just use words on the whole input. But that's not really going to teach us what we want to learn about right here. So concatenate is totally the way that we would go about it. It turns out that there's something really general, and Sanctuary uses the same name that Haskell uses for this, which is join. It doesn't have anything to do with joining strings. But if we look at its type, we might get an intuition for what it does. Okay, so don't worry about this chain M nonsense. Just look at the thing to the right of the fat arrow. It says M of A. That's what it takes as an argument. And it returns an M of A. So if I told you that M is array and A is string, then this is going to take an array of arrays of strings and give us back an array of strings. Essentially, it takes away one level of nesting from a nested data structure. So we could go back to the code that we had earlier and just add one more transformation, and we could get from our two-dimensional structure back to a one-dimensional structure. And that's pretty cool. But let's just have a look at a few of the things that we can do with join, because it's pretty sweet. So let's say that we had an array of arrays. This is the sort of bread and butter example, and we want to join it. We're going to take away one level of nesting. Let's say that actually we had I don't know whether this is called a three-dimensional array, but anyway, an array with one more level of nesting. It's important to know that join is not flatten. There's nothing array-specific about join. And so all it can ever do is take away one level of nesting. And if we start with something that's twice nested, we're going to get back something that's once nested. We're not going to eliminate all the nesting. But join, like many of these functions that we're looking at, is quite general. So many things are actually chains. Chain is the term that's used in the JavaScript world to define things that support flat map, which is this idea that we can map over a structure and also sort of smush the results as we go to avoid unwanted nesting. So let's just look at one more data type that we might map over. So let's say that we have a maybe that contains another maybe, and we want to eliminate that nesting. We can do that with join. And just as we saw with the array example, it's only ever going to remove one level of nesting. But the nice thing is we could join s.nothing and get back nothing. So it's just going to do the right thing. So it turns out that instead of mapping to produce this nested structure and then joining to get rid of the nesting, we could use a flat map operation which avoids introducing that unwanted nesting in the first place. So that flat map function in the JavaScript world is usually known as chain. So this is what chain does. It's actually, the type is very similar to the type of map. The one key difference is that instead of the function being A to B, the function is a to m of b. So if you think of, say, mapping with a function that's taking the length of a string, then this would be, a would be string and b would be integer. If we were to use chain, we couldn't use that same function as the first argument to chain. If we're chaining over an array, then the function that we provide as an argument to chain has to return an array in order to, to have a compatible type. So let's see how that can be useful. Well, that actually allows us to replace those two operations that we had a moment ago with a more direct operation, which is saying, hey, for each line, please get me the words and smush those words into the result that you're producing as you go. So chain turns out to be one of the coolest functions. Chain in Haskell is called bind, and it looks like this or something. Yeah, so chain maybe not the most intuitive name, but we can think of it as chaining together operations which may fail. Now, that's not really the case always, because we may just be dealing with arrays, and the example that we had a moment ago isn't really dealing with failure. But if we're dealing with the maybe type, then we really are dealing with failures. So this is a more difficult challenge, and we'll probably have a short break before we go too much further. So the challenge is to get the first element of a two-dimensional array. And that's, of course, trivial. Let's just define lists, and let's say, okay, foobar baz is going to be the first element, and quux. All right, lists, done. We can go home. But of course, you know what's coming. We can, in two different ways, make this blow up. There's, I guess, the slightly less bad way, perhaps, which is it's a non-empty array whose first element is an empty array. And if we evaluate that same expression, we get undefined. It's still pretty bad, because probably we wanted to do something with that value, and the next thing we try to do is going to error, and we're going to have to work backwards to see what went wrong. And it can, of course, fail in a more noisy way, which is when given an empty array, it's going to take the first value, get back undefined, and then try to access a property of undefined. And that's going to blow up. So I think we should have a short break. You're welcome to go outside, use the bathroom, or whatever. And maybe in the meantime, you can ponder, how would we get the first element of a two-dimensional array? We're going to need to use head in some way, but if we use head to get the first element of the outer array, we're then going to be stuck inside a maybe, and then, well, we might end up having a maybe inside a maybe, which might not be what we want. But I'm sure we'll get ourselves out of that mess. Cool, yeah.